It's a great pleasure to be here. So we're changing topics a little bit onto the carbon cycle. Now I'm playing on the right-hand side an animation of the geology globe for all those of you who aren't lucky recipients of the physical globe that you can put on the shelf in your living room. You're lucky that the G-Plates portal exists where you can access this globe and play it back and interactively. Now, the long-term carbon cycle. You probably haven't really heard of the slow carbon cycle. There's slow food, slow TV. There's all sorts of slowing down of processes being advocated these days in overall living. But the slow carbon cycle, well, it's something that a process that moves carbon around through the deep earth, ocean, and atmosphere over time periods up to 100 or 200 million years. So on average, about 10 to 100 million metric tons of carbon move through the slow carbon cycle every year. So in comparison, human emissions of carbon to the atmosphere are of the order of 1 billion tons per year, so much larger. So of course, human emissions are more important on short timescales, but on longer geological timescales, the slow carbon cycle matters. So what I want to do today is have a look at how tectonic models might help to constrain the slow carbon cycle, which is, of course, driven to a large extent by both tectonics and volcanism. And so first, we'll do a little excursion towards the solid plate models that we need to constrain these things. Now, there's a term that Chris Coates coined, which is motorboat tectonics. And that describes traditional plate tectonic models, especially back deeper in time, the sort of models that are mainly constrained by continental paleomagnetic data, where continents are moved around like boats floating on a mantled sea. And oftentimes you will detect motions of individual pieces in this puzzle that seem to be quite unlikely. And as soon as you actually start constructing plate boundaries, mid-ocean ridges, subduction zones, and transforms, you uncover lots of flaws in these sorts of models. And in the published literature, of course, they are often represented by just a few snapshots where perhaps some plate boundaries are drawn in tentatively. Right? And so we want to move beyond that kind of depiction of plate tectonics. And that's one of the many reasons why we have developed the G-Plate software. And so that's been an effort that's gone on now for over 12 years. It's supported by Auscope, which is part of the Australian National Collaborative Research Infrastructure System. And it's a global collaboration involving the Norwegian Geological Survey, the University of Oslo, and Caltech, of course. And here's Mike Gurnes shown in his natural habitat in Altadena barbecuing. And John Cannon and Michael Chin are the two primary developers, with Robin Watson at NGU also having made a major contribution, and Sabine and Simon here have played a large role in sort of designing plate models and providing input into these models. So really we are on a path. Of course, me not having been around during the plate tectonic revolution, I guess one of the goals I've taken on is trying to democratize plate tectonics, if you like, by developing an open source software that's available for the community that anybody can pick up and either just visualize or play back plate tectonic models, or also assimilate their own data and build their own models. Right? And so in particular, the software can be used to model plate tectonics with continuously closing plate boundaries, and it includes plate deformation. We can visualize the surface and the deep earth in 3D or 4D, and also include geodynamic model outputs. Right? And so quite timely for this meeting, this paper just came out 5 days ago in G-Cubed, explaining how G-Plates works. G-Plates has become quite popular. It's used in over 90% of all countries in the world, and it's become easier to have a look at where G-Plates is not used, which is done here. So there's a few holdouts, as some small countries in Africa. The Pope is not a fan, and nor is Kim Jong-un, you know. And these are all people. They're bogged down by non-plate tectonic problems, you know, which is kind of sad, you know. Yeah. Okay. So back to plate tectonics. So we've developed the technology that allows us to construct continuously evolving plate boundary networks. And that sounds quite trivial at the face of it, but it's actually taken many years because it's a semi-interactive procedure where geological and geophysical data are assimilated into a model piece by piece. These boundaries are essentially to be constructed by hand. And you see that they have these funny overlapping ends. And that's because each one of these boundaries will move around through time, and we need to ensure that they overlap, that no gaps are formed. And then G-plates will close them automatically and to create a depiction of plates like this. Right? And what's just been playing on the right-hand side here is a little animation that shows how we can now also embed deforming regions into these deep time plate tectonic models. So we've heard a few talks on the long-term efforts to build present-day plate motion models that include plate deformation. Especially Richard Gordon has pioneered that line of research. And so what we've done now here is we've developed the technology to carry these sorts of models into deep time. We're actually developing a global deforming plate model that's not quite finished yet, and that will include plate deformation in all major regions along rifts, passive margins, and origins where major deformation has occurred in the last 200 million years. And of course, this is just a depiction based on uniform lithospheric stretching or compression. We have no depth dependence here, right? So it's still a simplified view. And so, so this is how it works in G-plates. So we have rigid elements and sporadic fragmentary observations that constrain deformation, and we can then build these deforming meshes using Delaunay triangulation to connect the rigid blocks up to deforming regions. Right? And so we assimilate magnetic, gravity, and other geophysical data, like seismic data, into these models, stratigraphy as well, to define the extent of these deforming regions and also to define the age. That's done with stratigraphy and thermochronology. And so then we end up with present-day depictions of a plate model like shown here around Australia, where we can model crustal thinning factors. So what's shown here is 1 minus 1 over beta, the stretching factor, which is a nice property to look at because it scales linearly with synrift subsidence. And so we can then compare these models with observations, stretching factors derived either from crustal thickness observations or from inversion of tectonic subsidence data. Right? Or we can alternatively have a look at modeled crustal thickness by assuming a particular starting crustal thickness that the user can determine, and then have a look how well our model agrees with observed crustal thickness. Now here, this works quite well, mainly because it's an amagmatic or non-volcanic margin. For volcanic margins, this becomes more tricky because here you need to then use high-quality seismic data to try to first subtract material added by means of underplating. Okay, so I want to say a few words about our age of the ocean crust grid, which also forms an important component of the work that we've been doing. Of course, one of the handy things is that it includes an implicit definition of the boundary between continental and oceanic crust, which is important for our plate models. And so this was the first global age grid that we published in '97, so that essentially came out of my PhD, supervised by John Slater, seen in his younger years here on some DSDP cruise. I can't remember which one. And of course, Walter, who spoke yesterday, played an important role. I remember many days in Ottawa at the Geological Survey of Canada, where Walter was at the time, lots of cups of strong coffee to develop a Fortran program to develop this age gridding algorithm. And then Jean-Yves, who is, I think, also here today, played an important role in helping to construct the first set of isochrons together with Lisa Gehagen at UTIG at the time. And so in the meantime, this grid has been updated once, another update is underway. And of course, we've made immense progress with compiling data to underpin these models. There's now a public repository of magnetic anomaly identifications. There's over 100,000 pics in there by a multitude of authors who've worked on this and contributed their data. And that was put together by my colleague Maria Seaton. And the repository is actually maintained by Paul Wessel, another long-time collaborator of ours. And that's the Global Seafloor Fabric and Magnetic Lineation Database project that also contains fracture zone identifications. And so here some thanks are in order to Dave Sandwell, who's of course, well, he came after Bill Hexby, but David is sort of a pioneer who came up with some really ingenious methods to combine satellite altimetry data along track to produce these maps that we have then used to pick fracture zones. And Cara Matthews, my ex-student, is the one who picked all these fracture zones. And of course, here they're shown together with the magnetic pick. So this gives a nice depiction of the constraints we have in the ocean basins at this point to make these sorts of models. Right? Now, what I want to talk about now is the slow carbon cycle. Right? Now, tectonics drives the slow carbon cycle in a number of ways. There's degassing happening along rifts, and large igneous province associated with both degassing and weathering, and so they drive the carbon cycle in two opposite ways. We have degassing at subduction zones, degassing at mid-ocean ridges, and seafloor weathering. So I'm not going to talk about all those things, but I'm going to start with rifts. And so we were inspired by this paper in Nature Geoscience from a few years ago by Lee et al., who made the point that there are massive and prolonged deep carbon emissions associated with continental rifting. And that's the case not only along the East African rift, but also in the Basin and Range, the Ega Rift, Rio Grande rifts in central Italy and New Zealand. And so we looked at this global compilation of high CO2 flux along rift faults, and thought to ourselves, well, we have a global plate model that includes rifts through time, so we should be able to upscale this work and making some simplifying assumptions, come up with some first-order estimates of how CO2 flux along rifts has changed through time. And so this was done by Sascha Brune, Simon Williams, and myself. Sascha was on a Marie Curie fellowship at the time that he spent partly in Sydney. He's now back at the Geoforschungszentrum in Potsdam. And I'm just going to quickly flick through these images, and it shows two different depictions of rifts. The red lines are the rifts that are from our plate reconstruction, but there are a lot of rifts that are not in our reconstructions because they're relatively minor. There's hardly much extension that happened there, and so from a plate tectonic point of view, they're not very important, but from this point of view, they are important. And they were compiled by Sanger and Natalin in 2001. And so we combined them with our own reconstruction, of course, avoiding double counting or overlaps between the two. And as we flick through the reconstructions, the time shown here, then we see Sanger and Natalin's rifts with the size of these circles indicating the length of that rift system, and the lines are from our plate model. And of course, as Pangaea is breaking apart, there's a huge system of rifts developing associated with massive CO2 degassing. Then all these rifts disappear to a large extent as we have breakup and seafloor spreading happening. But then as we move into the Cenozoic, what happens is we create some new rifts, particularly the Basin and Range province here. There's a few rifts still active along the periphery of Asia. And then, of course, we create the East African rift as well that really gets going in the Neogene, right? And so this history of rifting, if we look at it over 200 million years since Pangaea breakup, so what we've done here is that's global rift length that's color-coded by region, and that's from our plate model, and the gray areas are added from Sanger and Natalin's compilation, right? And the takeaway point is that there are two peaks, right? There's one peak in the Cretaceous here, and there's another peak in the Cenozoic, right? And so what we did for this paper, we stuck these data into a global carbon cycle model, the the geocarb self model from Berner et al. That's now a dated model. I'm sure this can be done in a more sophisticated way. So these are two alternative depictions of rift length through time. The blue line here uses only Sanger and Netherlands data. That's one end member. And the red case combines our plate model with a subset of Sanger's data. Right? And in any case, so what's shown here below, the gray envelope is atmospheric CO2 through time. And you see it was high in the Jurassic and Cretaceous, it goes down, and then there's a high in the Cenozoic. Right? And at first order, that's reasonably well reproduced by our model. We produce a high in the Cretaceous due to all those rifts that formed when Pangea broke apart, and there's a high in the early Cenozoic. Now, what our model doesn't explain is why atmospheric CO2 content declined after sort of 30 million years ago, right? And because in our rift view of the world, it stays high. So we'll get back to that in a minute, right? And so now we're going to have a look at large igneous provinces. And so this is a paper that just came out a couple of weeks ago in Geophysical Research Letters. And that's Louis Johansen and Sabine, both from the University of Sydney. And so here's a satellite image of the Deccan Traps. Right? Now, the Deccan Traps is a nice representative example of these objects, and they influence the carbon cycle in two ways. Right? First, of course, there's degassing when they get emplaced, but the second one is silicate weathering. And the mafic and ultramafic rocks are particularly susceptible to silicate weathering, and this is how it works. So essentially, you get acid rain, CO2 gets dissolved in rainwater, and it reacts with silicate minerals, especially feldspar, forming new minerals, and CO2 is consumed along the way, and it's this equation that facilitates that. Now, it produces calcite and bicarbonate ions and dissolved silica, and they get washed into the ocean. What happens in the ocean, there's various pelagic critters that build carbonate shells, especially coccoliths and forams. Right? And so ultimately, funnily enough, these large igneous provinces end up on the seafloor as the remains of these pelagic creatures. Right? And so this is how, and the important thing is that the silicate weathering consumes 2 CO2, and the precipitation of calcite here only releases half as much CO2. So the net effect is a consumption of CO2. So we get rid of some CO2 out of the atmosphere in this process. And so this is an animation that's shown here with time running in the upper left, right? And the light green strip along the equator is the humid equatorial zone in which we assume that weathering is the most intense, right? And so we have various color-coded lips that are being erupted here through time. We have to watch this a couple of times to see what's going on. There's the Siberian traps. Red is the remain of camp that we've just seen introduced before. And then there's the Deccan traps as well. And so what we're going to have a look at in a second is both the effect of the degassing of these lips as well as the weathering. And the weathering is particularly being looked at here in terms of when lips pass through this equatorial belt. Now, there's some uncertainty in terms of how wide this belt should be, and we've tested 5, 10, or 15 degrees away from the equator. Right? And you can see right away that the Central Atlantic magmatic province straddled this belt for a long time, and we can very clearly see that signal in CO2 drawdown. And if we watch this very quickly for a third time, then there's actually not much happening in the Paleozoic. Lip emplacement really got going only around 200 million years ago. Well, it got going with the Siberian traps, I should say, and then with camp here. But the Siberian traps were not as severely weathered as camp because they were at a latitude that was remained quite high during their lifetime. So now we see the Deccan traps moving through the equatorial belt, and the Arabian African province in yellow there that just popped up. Right? And so these are two diagrams here showing degassing from the emplacement of these lips, but in a way these signals are perhaps less important in terms of influencing the carbon cycle than the weathering, because these are more short-term transient signals, whereas the weathering has an effect that's drawn out perhaps over tens of millions of years, right? And you can see how little there's left of camp today, and so that would have been a huge province at the time, right? And so, in the upper diagram, so we look at atmospheric CO2 content from a recent model by Foster et al. In Nature Communications through time. So there's time from 400 to 0 on the x-axis here. And so, so what we expect is when the area, so what's shown here in these colored curves is the area of lips straddling the equatorial zone, and the three different curves represent making this area either 5, 10, or 15 degrees wide away from the equator. And so what we expect is when the area of lips in the equatorial zone goes up, we expect CO2 to go down, right, because of this weathering drawdown of CO2. And we see, I think, that signal very clearly with camp. So camp is being in place and then weathered, and CO2 is going down, right? And we see that, and the second time when we see this effect very clearly is when CO2 is shallowing and then going down here. And we think that might be related to the Deccan traps and the far Arabian lip moving through the equatorial zone being weathered. And that's the missing piece that we couldn't explain with our rift degassing, I think, that this atmospheric CO2 drawdown in the Cenozoic. Now, the third and last topic that I want to talk about in terms of how tectonics drives the carbon cycle is subduction related. And so there was a paper in Science last year by a group from Cambridge. That's Emily Mason, Marie Edmonds, and Alexandra Turchin here on the right. And they looked at a global compilation of carbon isotopes from a subduction zone volcanics. And they concluded that crustal carbonate carbon actually dominates volcanic arc emissions. And they said, well, there must be a lot of carbonate that's either carbonate platforms that have been accreted to the overriding plate, or perhaps carbonate platforms that were once lining a passive margin that turned into an active margin. And so this carbon gets remobilized along subduction zones. And so we tested this idea in a paper that also just came out just a few days ago in Climate of the Past, and where we looked systematically at carbonate platform interactions with subduction zones since 400 million years ago. And that's led by another Sydney Uni student, that's Jody Pell here. And so what we did is we first digitized the global carbonate platforms from a compilation by Kiesling from 2003, and then incorporated them into our plate model. And we considered the carbonate platforms intersecting with subduction zones as long as they were within about 450 kilometers of the trench. And so that's what came out. So we started 400 million years ago. At 400 million years ago, we already have a few carbonate platforms. They're color-coded by their duration. So the longer they were live carbonate platforms, and the hotter the color becomes. Mostly the color is quite bluish and cool because most of these carbonate platforms only had a lifetime of a few tens of millions of years, right? And so there's already some carbonate platforms in existence in our model at 400 million years, and they, of course, originate in the lower Paleozoic and the Neoproterozoic. And the main effect that you see is that more and more carbonate platforms around as time goes by, especially after 200 million years. And this partly also reflects the evolution of carbonates sequestering marine organisms, especially pelagic organisms. And so here we see an animation that corresponds to this, right? And so we're now going to have a look at the time dependence of these intersections, right? And so again, there's time on the x-axis here, and we show atmospheric CO2 again from Foster et al. In the background. And in black is global subduction zone lengths, and then we split them up into non-carbonate platform intersecting lengths and carbonate platform intersecting lengths. And they're these two. And so we are particularly interested in the bold pink line here. And really the main effect that you see is that after 200 million years, there's more and more carbonate intersecting subduction zones around, whereas the non-carbonate intersecting ones are roughly stagnant, right? And so we then did a wavelet analysis. We did that for the lips as well. So a cross-wavelet transform is quite useful for this purpose because we can look at the time dependence of correlations in the signals that we are looking at. One is the atmospheric CO2 concentration through time, and then the various quantities, either lip weathering or, in this case, carbonate intersecting subduction zones, right? And as you might have already guessed from looking at this, the correlation is actually not great, right? And the only time we find a reasonably good correlation is in the Paleogene between 60 and 40 million years, when there's a distinct rise in the subduction zones intersecting carbonate platforms and the generation of a hothouse climate, right? And, but this is also a time when new rifts are being formed, and so the two processes might have worked together to create a greenhouse climate at that time, right? But the long-term increase in subduction zones intersecting these platforms essentially explain the observations by Mason et al., which is that today there's quite a lot of these locations where the degassing of carbonates on the overriding plate play a role in this context, right? And so, the conclusions so far are that, yes, plate tectonic reconstructions can be used to constrain time-dependent models of rift degassing, lip volcanic degassing, weathering, and subduction fluxes of carbon. Oftentimes, they're still quite difficult to do this quantitatively and to know exactly how fast lips are weathered, how fast their area decreases, and how much carbon is actually being released. But I think we are on the path now of constraining these quantities a bit better, and of course then they can be fed into global carbon cycle models. Another thing that we can also do, which I don't have time to talk about today, is we can in fact also constrain seafloor weathering through time as a function of the age of the ocean floor and how it changes through time, and bottom water temperature, which are the main two parameters controlling hydrothermal circulation through time. And that's, if you're interested, that's described in a recent paper with my co-author Adriana here in the paper in Science Advances. So I want to conclude with a few slides and that focus on deep time. I think there's a shortage of Paleozoic and Proterozoic plate tectonics at this conference. And so I thought, for good measure, I throw in this recently published model about a year ago of a full plate global reconstruction of the Neo-Proterozoic. And that was also written up in a piece in The Conversation, a map that fills a 500 million year gap in Earth's history. And so it's quite interesting. This article actually went viral. It was picked up by the ABC News in Australia, and it's been hugely popular. And by the same token, this paper here has been hugely popular. It's seen uptake in its first year that I've only seen anything similar in terms of Davis-Tandville's gravity map and related publications, right? So there's a large community, an active community, that is very interested in pushing plate tectonics back into deep time, despite the constraints for these reconstructions clearly becoming sparser. And so here we entirely depend on data from the continents and that we need to use to either restore the relative and absolute plate motions at the same time, incorporating paleomag data, of course, as well. And so that was done by my ex-student Andrew Meredith, who's now in Lyon. And Alan Collins, a collaborator at the University of Adelaide, has played a hugely important role here because he is a geologist with an immense global knowledge of the geology that constrains these reconstructions. And so I'll close with a few links to web pages where you can download resources to build your own virtual planet, in particular the Gplate and the PyGplate software, which is a Python library where you can include various plate tectonic workflows into Python scripts. And there's, of course, the Gplates portal for interactive virtual globes. Then you only need a web browser to have a look at these reconstructions. That's what's shown here, running in the background. is Andrew Meredith's global reconstruction, which is the first reconstruction with continuously closing plate boundaries that starts at 1 billion years ago. And of course, you can easily say this is completely wrong, and it is most definitely completely wrong, but it is a starting point that now other people can pick up this this model, and they don't have to start from scratch, and they can gradually improve it in various ways. Thank you.